or numerical integration problem. We firstly consider two kinds of questions. The first kind is the integration. All of them are the integration. The first one is f of x dx. Now, if the interval, the length of this interval AP small. This kind of length is very small. For example, f of x and length AB. How can we do integration? Okay, so this in this case, the integration, as we have discussed in last class, we will find a simple function, or sometimes a base approximated or interpolating function, called P of x here, right? Then we replace this kind of integral problem into a new question. We use P in because the function formula of this f of x is sometimes complex, so we change to a simple function. For example, this P is easy polynomial function, but this P should be sometimes the based approximation of this one. We ask this one to be the based approximation, because there will be lots of polynomial function with degree in the set, right? So we may need to find the base. Okay. If we use the base approximation, we may solve a linear system to get this coefficient of this one. Okay. This is base approximation. On the other hand, we may use the interpolation technique. So we directly construct this PN. Sometimes we call this is create. Right? We can create this kind of polynomial function directly based on our interpolation technique. Here we have started Lagrange method and Newton method. And also right?
Yes.
Okay. Now for a very small length, this kind of function may be chosen as specifically you may choose the polynomial function with degree 1 or polynomial function with degree 2. That is okay, right? Because the size is very small. So if we choose polynomial function with degree 1 or 2, and we take this kind of method, we may directly write the formula of this function. Right? Okay. Before we write the formulation of this function, before we construct this kind of function, we need to define the node point. For example, x0, x1, or x0, x1, x2. Right? In practically, if we choose just x0, x1, so we may take x0 equal to a, x1 equal to b. Right? If we, that means we just consider this interval as one partition. If we partition this interval to two parts, if we partition this partition to two parts, we may use x0, x1, x2. In practically or in our experiments, we may use x0 equal to a and x2 equal to b and x1 equal to 1 a plus b over 2, right? And this kind of participant and this kind of participation or the length of this node points is called equi space. Right? Equi spacing. That means here we ask x1 minus x0 is equal to x2 minus x1. Right? Usually we may choose this kind of participant. That is x0 is here, x1 is here, x2 is here. Right? Okay. So if we do some partition, the first one and the second one, if we do the partition like this, we may directly write the formulation of this P1 and P2. Okay, if we write this one with the partition like this, so the function of P1 of x will be write as, of course we have the function value. This one is x0, x1. Here we must have y0, y1. So here it will be x minus x0 minus x1, x minus x0, x1 minus x0. I think all of you can write this kind of Lagrange interpolation polynomial function here. So like this, here we may have y0, y1, y2, x minus x0, 1, x minus x2, x0 minus x1, x0 minus x2. Here should be x minus x0, x minus x2, x minus 1 minus x0, x1 minus x2. Right, plus x minus x0 right. Okay, so this is the polynomial function with degree 1, this is the polynomial function with degree 2. If we choose this kind of two functions here, we put to this one, here we may get two kinds of approximation. We use n equal to 1 or n equal to 2. Specifically, we will have the direct formula. If we take this from this one, last time we have directly proved x here is a, b, and is y0, is y1. Exactly here. Here is x0, here is x1. Right. Okay, we will get we get the formula like this. Is x0, x1 minus x0 over basically if we denote by step size of this one here with h, we will get basically fx0 plus 1 or fb, right? So we will get this kind of formula, and this formula we call the trapezoid rule. Right? Okay. We have discussed last time. Okay. This rule is here. We just use a linear function to approximate this unweighted function f of x, because the length of this interval is very small, so we will just take this kind of method. Or if we use the polynomial function V2 or the quadratic polynomial function, here will be write as now we may put this part to here. Right? Okay. If we put this part to here, that is called Simpson's rule. Now the step size here should be here h is equal to b minus a. If we take this kind of spacing here, each of we call it h. This for this case, h will be 3 minus a over 2. Right? Because we have two partition. Okay, here is just 1. So if we use this kind of method, we may do some integration for this function. Here is the function will be V2. If we directly use this kind of method, we may get this one. We directly do integration, the first term, the second term, and the fourth term. Now we do not discuss the residual error. Okay, next we will discuss this term later. Okay, so we truncate this part. We will directly do this part. Then we will get the Simpson's rule. Okay, we may the derivation. This part you can directly to derive this one, or use this kind of technique. This is automatic direct derivation. Okay, this makes sense for you. Okay, and finally we will get this one. Okay, okay, this one. This is called here. Here we use H bar, because this H bar is not that. Okay. And in the fx0 plus 4 times fx1 fx2. Okay, like this. Okay. The residue error will be discussed later. Okay, this kind of technique we call the Simpson rule. here we use just 2 points, and here we use 3 points. Sometimes this method we may hold the 2 point method or 2 point this one. 2 point for this is sometimes 3 point. Right? Okay. We directly take a look at why this part, this shape is the whole. Okay, let's take a look at the idea. Now, we directly to do Taylor expansion. Okay, to generate expansion for the f of x. Here, f of x to Taylor expansion and the x1, right? This one can be write by yourself. Okay, just the Taylor expansion. Now, if we truncate this, there must exist cx. This c is related to this x. Okay. Now, if we do integration x0 to x2, and f of x, we maybe write like this formula, and here is we put f of x this part to the inside and do integration. We may get these 2 terms, these 2 parts. The first one is this 3, 1, 2, 3, 4, this 4 part. The last one is the last part. Okay, this part is the residue term. These 4 terms is the useful terms we may use. Okay, and we do rearrangement this part. We do rearrangement of this part. Okay, this is error analysis. We do not discuss because h is the length, half length of this one. Here, this bar. That's this bar, right? Okay, and we may directly write this one like this. That is this here in this part. Here is x minus x1, x minus x1. Okay. Okay. So we may have this formula. This formula is get from this one, get from here and here, and this term is because this cx is just a constant. This constant is related to x, but this is not a variable. This is not a variable. That exists c. Okay, it's not a variable. So the inner part we do not. This is constant part. So we just do integration this part. So this is the error part. Okay, why we check out this term. You can take a think why we consider this term is a constant, because here if we do Taylor approximation, c belong to x0, x1. I think we may skip here quickly. If you want to do more discussion, you may ask to do some more attention here, right? Okay. So we may directly rewrite this residue part to this one. Okay. And the other part here, the other part x minus x. Here with x0, x1, we put x2 here, and x0 here. We must have x2 minus x1, x2 minus x1, x2 minus x1, x2 minus x1, and x0 minus x1, x0. So here it's x2 minus x1, x0, x minus x1. So we have this one formula, this formula. And to rearrangement, we will get this one. Okay, we'll get this one. And this f, the second order derivative is replaced by approximation. Okay. If we put these two parts here, this one, f here may be replaced by f of x1 minus x0, x1 minus x0, right? And this one may be revised as like this to approximation. That is numerical. This is numerical differentiation. Okay. So we may replace these two terms with function values, with just function values. Okay. If we replace these two terms with function values, here we may lose this one, just have the function values. Okay. That is, you write here, write it. So this one will be right here, and we get the formula. Okay, this kind of formula is sometimes simple. Okay, but the duration is usually very complex. Okay, it will also show you in our table. Just leave this slide for you. Okay. So we need to remember, if we have 3 points, that is x0, x1, and x2. The formula is called the Simpson's rule, and this one can be written as the first function value is the last function value, and the middle function value. The middle function value we take 4 as a coefficient. Now, this dual has a condition. This condition is equi-spacing. That is, we have 3 points, x0, x1, and x2. And all of these belong to A and this interval AB. And we ask, x0 equals to A, x2 equals to B, and x1 equals A plus B over 2. Here we means x1 minus x0 equal x2 minus x1. This is the condition. Under this condition, we get this kind of formula. Okay, this is very important. It's equi-spacing. Okay. In your future study, this kind of spacing may not be equi-spacing. Okay, if we ask you to find a higher order spin or rule, you may to find a new spacing spin. Okay, that means here we spacing this AB. Take this is x0, x1, x2, right? If we just take x0 here, x2 here, and x1 here, what happens? Okay. This is x0, this is x1, x2. They are not the same. The spacing is not the same. Sometimes we make it a more effective method. There exists more effective method. That calls the Gauss method. Sometimes we call this some conditions, this kind of point, or growth point. Okay. This part we may discuss in our lecture, but they reached, okay, usually this point is very more important than this one. But this equispacing technique is very simple, and we may remember, and it is easy to calculate. Okay, if we take these two rules, okay, for the very small length, okay, and this the first the one is avoid rule, the second is the Simpson's rule is very simple. It's just that we take two function values to summation and take a half of the multiply the coefficient with half of the length of the interval. That's okay. And this one we just take the first and the last function values and plus the middle function value with 4 times. Okay, then do multiplication with this coefficient. And notice that here the space is not this one. It's half of this one. Right? Okay. This is for the shortness of the interval. Okay. Now, if we take a long length of the interval, now if AB, the interval size or the length is very large, that means, for example, AB here, and the F like this, right? So in practical, we may meet this kind of question, right? So this is just very small length, but in practical, we may meet this kind of question. Now, can we take the trapezoid rule? Just use a function like this, P1 of x, or takes the Simpson's rule. We take P2 of x like this. Okay, this kind of tool technique may take a huge area. So the area is very large. So in practical, for this large length of the interval, so we need to take another technique. That is, firstly we do partition. So we first, step 1, we do partition. And that means with a lot of part. At each very small part, okay, for example, this is called x0, x1, x2, x3, x4, xn. Okay, because here is x0, x1, we have n part. Right? We have n part. Each of these parts we take the equipartition. If we do equipartition, so here we have xn minus xn minus 1 equal to xn minus xn minus xn minus n xn minus 2 equal to x2 minus x1 equal to x1 minus x0, right? Because we do equal partition, if we denote this kind of step size is h, okay, if we denote this step size is h here, okay, at each of the very a subspace, subinterval. We call this subinterval, right? This is subinterval. We apply the trapezoid rule or apply the Simpson's rule. What will happen? So first we do equal partition, then step 2. We apply the trapezoid rule or Simpson's rule. If we apply these two rules, what will happen? Now the question I equals to AB f of x dx will transpose to summation, right? K equals to 0 x0 to x in right, okay, and each state is xk plus 1, and here is f of x dx. Okay, if we apply the first is trapezoid rule, the second is Simpson's rule. Let's take a look at what happens. Okay, if we apply the trapezoid rule for this interval at each of the subinterval, okay, so this will equals to summation k equals to 0, 1. Okay, now we replace this part. Here is just approximation, right? Okay, if we apply the trapezoid rule here, must have h over 2, right? H over 2, and the inside is f of xk 0, 1. Minus 1, right? Okay, we just have, right? We have in part, k plus 1, here should be n minus 1. Here c y, here should be x k plus f of x k plus 1, right? Okay. Specifically, it becomes 2. This should be right. The first, okay, all the inside is different, but the outside has this coefficient. So we take this coefficient out. So it should be h over 2. Now, summation, right, is k equals to 0, k minus 1, is f of xk plus f of k xk plus 1, right? Okay. H over 2. Okay. Let's write this summation step by step. The first one is f of x0 plus, in the first interval, this is f of x0 plus f of x1. Okay. In the second interval should be f of x1. Now k equal to 1 plus f of x2, right? In the third interval, f of x2 plus f of x3, and so on and so forth. At this interval, it should be f of x n minus 2 plus f of x in minus 1, and the last interval will be f of x in minus 1 plus f of x in, right? Right? Because at each of the sub-interval, we have applied, right? Okay, so this is right. Great. This is great. Now take a look at these summations. This is the first summation. This is first function value. This is the last function value. But at each of the middle part, it has appeared 2 times, and here it appeared 2 times. So this term should be appeared 2 times, and this term should also be appeared 2 times. This term should be also appeared 2 times. So now we have h over 2. The first is f of x0 just 1 times. The last is f of x1 just 1 times. But in the middle, k equals to 1 in minus 1. F of xk has appeared 2 times. Right? So this is now we successfully transpose this kind of integration to some summation of the function values. Okay, but here the step size of this h is equals to what? Equals to x1 minus x0
divided by
right? Because we have partition part, this we do equal partition this whole interval to n part, right? So each of the parts should be equal to right? Yes. Okay. So each of these one is here. So if we substitute this one to here, it will be two a minus 8, right? So this is the whole technique for the long length of the interval. If we apply the trapezoid rule to this long interval, long step size, long length interval, the integration, so this is called the composite and composite. Here's composite Simpson. Okay, here is the composite trapezoid rule, right? This is called the composite trapezoid rule. Okay, this is called the composite trapezoid rule for the long length numerical integration, right? So this is clear. This is the same to this one. Okay, the error, the residual error discussion will be shown later. Okay. Now, if we apply the Simpson's rule here if we do not use trapezoid rule, just use the Simpson's rule, what will happen? So if we apply the Simpson's rule here, it will be k equals to 0, a minus 1. And here h is equal to x1 minus x0. But if we apply the Simpson's rule in this small interval, here we need 3. We need 3 points. This is 1, this is 2, and this is the middle, right? So here we must use, here is h, here is, we need to use h bar, right? This h bar is the half space of this small interval. It's half of the small length of this interval. Here is over 3, directly, right? Here, this one, right? So the inside should be x k. Here is plus f x k plus 1, and we have 4 times f x k plus 1 over 2. Right. This point, this dot point is the middle point. Here we call xk is xk plus 1, right? This is called xk plus 1 over 2, right? Okay, so we have this term. This is the Simpson's rule in a small interval xk plus 1, right? If we do rearrangement, this is the same. This is constant term, so we put that, take this term outside. Here we take 3. Okay, now we do summation inside k equal to 0 in minus 1. Okay, this is f of xk plus 4 times f of xk plus 1 over 2 plus f of xk plus 1. Okay, and specifically we may have 3. Now, in the first, okay, we may take a break and we each of the subspace, subinterval like this. We have 3 points. We may get this kind of summation, and we specifically write each summation here is f of x0 plus 4 times f of x1 over 2 plus f of x1 plus, this is the approximation in the first interval, and in the second interval here is to be f of x1 plus f of x3 over 2 plus f of x2, right? Here should be 1 plus 1 over 2. This is second interval, and the third interval is f of x2 plus f of x2 plus 1 over 2 plus f of x3, and so on and so forth. The last interval should be f of xa minus 1 plus, sorry, there is 4 here, there is 4 here, and there should be 4 times f of x in minus 1 over 2 plus f of x in, right? And we also notice that h bar, here h bar should be x1 minus x0 over 2. And this x1 minus x0 is equal to this one, so this should be right? Like this one. So we put this h bar, substitute this h bar to here. There should be 6 in b minus a. The inside is the first function value appears once time, the last is once time. In the middle, in each of the middle points, we have in one each. At each of the sub interval, we have a middle point. We have in one. We have in middle points. Here should be summation. We can take coefficient 4 outside. Here should be summation. K from 0 to n minus 1. Or here is f of xk plus 1 over 2, right? And each of these middle points appears 2 times, right? This is 2 times, this is 2 times, 2 times. So here is 2 times. We do summation k from 0 to minus 1, or there is 1, there is can be 1, the middle point minus 1, there is f from xk plus 1. Okay, so this is called the composite Simpson's rule. We have the formula here, right? The same with this one. Okay, this is called, here we have 3 over h, but here this h is, here should be a mistake. This h should be 6, right? Like this. So this one. 6 b minus a over n times 6. Okay, this is the composite. We need to remember these 2 formulas. Okay. If we approximate this numerical integration, this formula is called the composite trapezoid rule, and this one is called the composite Simpson's rule. This is h. So here Simpson's rule should be a half. This is Mr. 2, right? Here should be a half of this one. Okay, here. From here we know this h should be the half length of its unit, right? So this h is this one. This h bar is this one. Okay. So at each here should be a mistake, I think, right? Here should be 6. If we take this one, h is b minus a over n. Here it should be 6. Okay. Oh, here is not. This is 3 because we participate this thing of yes. Here should be 6, not 3. Right? Should be 6, not 3. The notation for this one, we use this kind of notation sometimes not clear. I think this kind of notation is more clear. Okay, let's take a look at some example. For example, if we ask you to apply the trapezoid rule and the Simpson's rule to calculate the numerical integration for this 1, 2, 3, 4, 6 functions, and the interval is 0 to 2. If we directly use the trapezoid rule and the Simpson's rule here, this is the trapezoid rule. We just truncate the residual terms. Okay, we will get this two formula, right? And if we substitute x squared to f log x, and we can directly calculate this one. Okay, and then if we substitute x power 4 like this, and we can directly get this approximate. This is approximate value, and this is exact value. It seems the Simpson's rule is more more accurate than this trapezoid rule, right? Okay. So Simpson's rule has less error. It seems. Okay. Here, for the composite Simpson's rule and composite trapezoid rule, we have not shown you the example here, but you may ask to do exercise by yourself to find the example to train yourself, because this kind of question may appear in your final examination. For example, I ask you to calculate numerical integration 0 to 4, and f of x is x square minus x plus 2, for example. And this one, if I ask you to apply the simplest composite trapezoidal and Simpson's rule, to calculate it, we do approximation to compute numerical integral for this one, and I ask you to equipartition. Do equipartition is, for example, here is 4 subintervals. So how can you calculate this one? Right? It's very easy. just apply these two formula, like this one. For example, we apply the trapezoidal rule directly here. I equals to 0 to 4. Then it's x squared minus h1. Then it's plus 2. Right? Okay. If we apply the composite trapezoidal rule with 4 equal partitions. So here should be, so the interval is 0 to 4. If we participate this with 4 partitions, so the h, the subinterval, the length of the subinterval h directly apply this formula. Here should be
B minus A.
n equal to 4. So it's b minus a in 2. Here is f
B
0 plus
the summation
f4, right? So the interval 0, 4, if we participate then to 4 in subintervals, here this is x0, x1, x2, x3, x4. So there should be 2 times f of x1 plus f of x2 plus f of x3 plus f of x4, right? You directly calculate this. B minus a is 4, right? N is 4. So you can calculate this one. By the calculation, you may take calculation to our final examination directly. This is definitely. You just put 0 here, 1 here, 2 here, 3 here, 4 here, and you get the final answer, right? Okay, you are required to know how to calculate this kind of question. Okay, this is for example, this exercise. This is a very simple example, but this is more complicated. This kind of example may appear in our final examination. Okay, now take a look at this example. From this example, we may find that it seems the Simpson rule is more accurate than the trapezoidal rule because this is exact value. This value is to integration, right? To integration. Okay, this Simpson's rule is more accurate than the trapezoidal rule. Now we may ask you why is this rule is more accurate than this one? The reason. Okay, so we need to do some error analysis. Right? We need to do error analysis. The reason is here because we still first we do discussion at the small interval. Because here we use P1 of x, Here we use P2 updates. This is the reason why the Simpsons rule is better than trapezoidal. So let's take a look at this one. Okay. Here we have two kinds of approximation. The first is you here is P1 of x, here is P2 of x, right? Okay, so if we consider the residue, we do minus these two terms, it should be here is P1 of x, here is P2 of x, right? Okay, this is called the residue. This is called the residue. Now recall the error analysis in our Lagrange interpolation. Okay, so this is the residue term. This is the residue for the polynomial function with degree 2. This is the residue term for the polynomial function with degree 1. So here should be here is called R1 of x, R2 of x, right? Specifically, it equals to anybody remember what is the formula of this? This is the general case. Rn of x equals to f of x minus Pn of x is n plus 1 right? This is the general error. So now we put these two terms here. We put R1 here is 1, here is 1, so here is 2. You see? This term is related to x, but this is a constant for this integration. So this is x minus x0, x minus x1, eta x, right? So this is eta. It's also related to x, but for this integration, this one is constant. So here is x minus x0, x minus, here is x2, called x minus x1. Okay, we assume the here is x0, x1, x2. This is the trapezoidal rule. This is the function will have a middle point here. So
X mean x1.
so we need to analyze what's this happens. What's this? Right. Okay. The error terms, the residue terms is discussed. That's this term, right? This is the residue term, the same. Okay, 1/2, this is the residue term. Okay, what is the value or the size of this one? Okay, so let's consider this term. Here is x1. We also use x1 here. Because this kind of technique is use x1. This x1 is x0, x1 is AB. Okay, for this also AB. Here this is x0, this is x1, and this is x2. Right? Okay. So this term, specifically, what's this term? If we denote the length of this interval is h, this is h, this should be h bar. Okay, so we need to analyze what is error related, residue related to this length of this interval, right? Because in the next we may apply the composite technique. Now, if we ask you to get a very high accurate formula, you may ask to participate this to a density partition for this one with very small step size. Okay, sometimes this one. This is the length of the subinterval. Sometimes it is also called step size. Okay. So for this one, because this is constant, so we may take this constant term outside and do integration just for these two terms. But in this function, it is a polynomial function with degree 2 related to the variable x. So this is 96. Okay. So we may directly do integration because this is just a polynomial function. Okay, we can do integration like this, and finally we calculate this integration as this formula. Okay. This we put we specifically here is x squared minus these two terms times x, and plus these two terms, and if we take x0, x1 here, and we get this term. Okay, this step we may not show you specifically. Okay, I think all of you can calculate this one. Okay, so we may get this h. This h is just b minus a. This h is just b minus a. So this one should be approximately to here is h equal to minus 6. Right? We have this one. This is so if we ask you, because this is constant term, we cannot control this term because the function may be variant, right? So if we ask you to make the residue term is very small, because this function is annually, or sometimes the twice times derivative is cannot be controlled. So we may control this one. So if this h is very small, the residue is small, but the order is 3. The order is 3, right? This is the order. So first, if I take h equals to 1, so the residue term is h1. Now, next time if I ask you to point 1, so the error should be, so this kind of error should be in this one. So this kind of error should be this one. Right? is -3. Okay. Now, how about this one? The residue of the Simpsons rule. Let's take a look. For this is here we just right. Okay. Here still missed 2 here. So here still. Right? Because here we lost 1/2. Here is 1/2. Okay. If we put 1/2 here, it is minus h. Here is 12, and here is 3. Okay, if we apply the Simpsons rule, similarly we need to estimate this term, right? Here, this term is also a constant. We may take this constant term outside and do integration for this polynomial function with degree 3. Okay, directly we may get this one. Okay, this is this one, right? Here is 19. Here is h is 5, right? Okay, similar to this trapezoid one, this term is constant. So this one is also constant. Right, this one is 3. Okay, 3 terms here. 4 and 5. Okay, so if we apply the trapezoid rule here, h has the power is 5, here is just 3. So if we at the same time we take the size h equals to 1 minus 2. So this value has the length minus 6. But this one 10 minus 10. Right? But here h is h bar is not the same with this h. So here should be h bar. Okay. Here h is h bar. Is this one. Okay. 19. So this is why here we have the main difference between this is constant, this is constant, this is constant. All of the constants have very small influence, but the main influence is this term. Here is 3, here is 5. So if the space, the interval size is very small, it's smaller than 1, okay, it's smaller than 1. So this term is, the residue term is very, very small. This is why here it seems Simpson's rule has more accurate than trapezoid rule, because the residue is very small. Now let's take a review. Because we have applied the interpolation technique, so we have this elliptic formula. We have this elliptic formula, we get the trapezoid rule and the Simpson's rule for different technique of the partition, okay, and for the composing. So this formula is very simple, and we can calculate quickly by ourselves, right? This is why we apply the interpolation. If here we apply the base approximation, that is the base least square approximation, so we may do not have the elliptic formula of this one, right? And these terms cannot be given quickly. Because for the base approximation, we need to solve the linear system to determine the coefficient of this polynomial function, right? So for the base approximation, we do not have the elliptic formulas, and we cannot do analyze based on the residue, right? So this is why we apply the interpolation to do numerical integration. We do not apply the base least square approximation. And the reason is for the interpolation we have this specific formulas directly. Okay, but if we apply the base least square approximation, we cannot get the formula of this polynomial function. Okay, this is just for the small length residue we analyze. Now, if we check this one to the composite part, so each of these parts will have a residue R1. Each of this part has R2, R3, right? If we change, if we substitute all the residues to this composite part, what will happen? Here is R1, the remaining part R1, here is R2, here is R3, here is R4, Rn minus 1, Rn, right? So the residue terms may have maybe the summation of this one. So what is the total remaining of the composite trapezoidal group? What is the total remaining? We need to do discussion about the total remaining. We just take a look at the total remaining part. Okay, so the total residual part of composite trapezoidal wall is now the total remaining is the summation that is from from 1 to n. There is RP, right? So the total remaining should be k from 1 to n is minus h3. Here should be ck, right? Okay. Okay, if we, because this one is constant, this one is constant, this one is constant, right? This one constant, this one constant. This one is not constant. So we put constant outside. Here is h cubic. If we check h cubic, to every discussion. For the we can directly A is minus 12 h squared h cubed a equals to 1. In here, if we, this is ck, right? If we take the mean value, so because we have here is fc1, fc2, fc3, fce, so we may have many this one. So if we take this is the summation, okay? So we put this one, this is 2 here, and this h here. What happens? This is sometimes just because time, so we will just discuss this one. What happens? So this comes to 1. Here is 12. Here we'll put 1h here. So here is h squared. So this is summation times the step size, right? The summation of this one times step size just this one. So this is just the integration. This is summation. If we put this h is very small, this is integration, right? And this one, if we take this one as the mean value, this is take mean value, right? If I take mean value, this one should be take the mean, right? If we take mean, because if we take f mean, c equals to in this one. Right? If we take mean of this one, this is mean. So this becomes constant. Right? This is constant. So if this is constant, so we can take this term outside. Right? So we put this term outside, it will happen. H squared is 12. Here is constant. We may take this constant outside. That's the mean value theorem, right? It must exist one constant equal to this one, right? So here is just b minus a, right? Because this constant outside here just remaining 1 here, right? This b minus a. Now the order is reduced to 2 for this one, right? Because for the single interval, here the order of the residue of the, because the order of the trapezoidal method here is h cubic, right? But for this composite trapezoidal rule, here's the order. After our rearrangement and reduction, okay, the order reduced to 2, right? So this order is less than composite trapezoidal rule has the order less than the direct use of the trapezoidal rule. Similarly, for the composite synthesis rule, of course, must reduce to 4, right? Because this for the composite is reduced to 2, for the trapezoid should be reduced to 4. Okay, here is 4. We get 4 here. And similar technique, right? Why we have 4 here. Okay. So this is the reduce or the error analyze or the residue for the trapezoid. So for the composite Simpson rule, here is H4. For the trapezoid rule, the error is 2 here. Okay. So this rest term we have here. Right? Here, this is from here. We just do very simple analyze. Okay. here is just a theorem direct given for you, but how to prove this, I think we have this block and this block, we can get this one, right? Okay. This is y here is square, is not cubic. And that is the same here. Okay. Here view is just the mean C. We have notation, we have different notation, but the idea is the same. Okay, you may apply this kind of idea to get this result. Also, the detailed proof you can find in the electronic textbook by yourself, but the idea is the same. Okay. So I think today we will stop here. And next time we will have a picnic break. Quickly take a look at the numerical differentiation. I will explain. So you are asked to do example exercise by yourself for the composite trapezoidal form to calculate a specific question. Okay? Yes. Stop here, class over.
Okay.
Thank you, Bob.